final talk in this session is on Lurk, Lambda, the ultimate recursive knowledge. And it's by a bunch of authors, but the talk is given by François Garillot.
Hi, thanks for coming to this talk. I'm François Garillot, and I acknowledge to all my co-authors on the screen and thank the organizers of the conference to invite me to present this paper. So this paper is about a general way of scratching my own itch about verifying the correctness of a computation without having to redo it. A long time ago, more long time than I care to mention, I did my PhD thesis in the project that led to the formalization of the Fate-Thompson theorem in Coq. And this is a contribution by an author, a user I don't know, that described the experience of actually verifying the Fate-Thompson theorem proof, which amounts to downloading a big program and then running the type checker for 2 hours. And 2 hours is a bit long. It's a bit painful. Wouldn't it be nice to have the ability to create a proof artifact that's asymptotically faster to verify than redoing the type checking? Turns out there's even the description for, there's even a solution to that problem if we want to apply it to another problem than type checking. Let's say we're redoing any computation. And then there's even a cherry on the cake, which is, what if you want to be Fermat? What if you want to demonstrate that you have a valid proof of a theorem, but withholding the proof, yet convincing people that the proof exists and it is worth looking for centuries? And so this talk is about, yes, how we did scratch that itch. Yes, but it's actually not about that. I'm not going to have time to express the details of how we wrote a lean type checker in a zero-knowledge proof system. You'll have to read the paper for that. But what I'm going to talk about is that we did it at the cheap cost of writing that type checker in Lisp. And actually, it was Lisp just as an artifact of us having to engineer something. It could have been any general purpose functional programming language. And interpreters that define those functional programming language have a role to play in the cryptographic context. This year, and especially because we've made them, brilliant cryptographers have made them relevant. It's how we built one, how it had to be, that interpreter had to be shifted for the cryptographic context, and we would like the help from the community about everything we're doing wrong. Warning, this is not, while I use a theorem proving example, this is not a talk about theorem proving. This is a talk about zero-knowledge proofs in the cryptographic sense, which I'm about to detail. Okay, so zero-knowledge proofs are a protocol that involves a prover and a verifier that work adversarially together. The prover creates a proof of satisfiability of a formula, and that proof is a bunch of bytes, passes them on to the verifier. The verifier reads those bytes and then has a way to decide whether the proof is valid or not. Traditionally, you present it as a proof of computational integrity. So you have a function f that you'd like to compute over some inputs x and w. And you want to check that it produces an output y, right? It's a proof of satisfiability in order to get to the zero-knowledge part of the zero-knowledge proof. In the W here, which is traditionally called a witness, can be something that is withheld by the prover. The actual protocols for creating those proofs is constructive. That is, it's very difficult for the prover to create a proof without having the actual witness W. So the prover tells you, I have a witness W such that f of x and w is equal to y, but I'm not telling you about w. You have f, x, and y, and that's all you verifier can work with. The protocol is sound and complete. Sound means you can't cheat the verifier. Complete means you convince the verifier in the end. But there's one cost to all of those cryptographic protocols, which is that you need to express f as an arithmetic circuit. The fundamental reason for that is in the math that are being used that lead to polynomial identity testing. And I'm describing a wide range of protocols that have this constraint. But once you've done that expression of your computation as an arithmetic circuit, you get other cool stuff. Other cool stuff include succinctness. Verifying the proof gives you an exponential discount in redoing the computation. That's it. We have our cheap type checking without having to actually rerun the type checking. We just verify a run of the type checking. And the other cool thing is you can get zero knowledge if your witness is actually valid and something that you're really interested in. Hence the classical name SNARKs, succinct non-interactive argument of knowledge that you will find in every cryptography paper. Okay, arithmetic circuits. Arithmetic circuits look like circuits. They have batch equality constraints at the end, but basically the only primitive types you have are finite field elements, and the only operations you have are addition and multiplication on those finite field elements. Now, the nice thing is that we have good calculability results telling us that you can encode the trace of any computation here. The not so nice thing is that I just said one word too many for the Turing completeness we all know and love. I just said the trace of any computation. What does that mean? Well, there are already DSLs that compile relatively simple programming language into circuits. There's 5 of them on these slides, there's more. And the general approach of how you would go about doing that is to say, hey, well, we're going to break down the components of your source language, and we're going to step-by-step translate every instruction into ad hoc combinators that translate whatever semantics on integer or strings that you want to model into things that happen on finite field elements, right? Except arithmetic circuits, your compilation target in this task, is a flat structure. It requires completely flattening everything. You have no control or jumps or anything even remotely like that. That means we can't go into the detail, but just to give you a flavor of this, it means unrolling all of your loops, and it means you have interesting problems when you want to branch. And what that means at a deeper level is that arithmetic circuits are a non-uniform model of computation that really encodes traces of computation rather than computation itself. So one example of this is that this is a Lisp expression of the function that computes the Syracuse recurrence. And it is the subject of the Collatz conjecture whether the Syracuse recurrence terminates for all inputs, which means you cannot unroll loops for this function expressed in open form. Once you have it in closed form, that is for a certain number of arguments, yeah, you can unroll, if at least the conjecture is correct, but if you give me one of the inputs for which it's reasonable to unroll it, then yeah, experimentally you can do it. But for any input, it's impossible. Another thing that's difficult to compile to circuits is an even simpler function. You want to branch? Cool. The whole point of this proof is to verify constraints. If I don't have any alternation, I can't verify constraints on just one branch of my program. So if I have a division by 0 on one branch of the program, that proof is invalid, which means there's serious messaging needed to bypass a direct or to generate a computation of this in a circuit. Okay, so direct computation to circuit, not really fantastic. Traces are not a great thing to compile. Is there something better? And the answer is very recently there has been something better. There's a general framework which is basically the way cryptographers talk about something that is familiar to most everyone in this room, which is a Y Combinator. They have been talking about this in the terms of IVC, incrementally verifiable computation, which says if you have a function that you can break down in n individual but identical steps, you can verify it piecemeal using incremental proofs. Traditionally, the way you would engineer it until very recently would be full-fledged recursion. That is, you take the verification protocol, and that verification protocol is itself computational. It can itself become a function. So you express that verification in a circuit, and then the computation you choose to verify on every step is that the verification of the prior step returned true, and the new increment, that is the new step, of applied to the output of the prior step and some secret witness returns the output of the next step. The problem with that, expressing your verifier in the form of a circuit makes this computationally extremely expensive. So I think we're all clear on how this is a Y Combinator. This allows you to do recursion. The thing is, we didn't know how to engineer it practically. So that's basically what this looks like. I take the same function, and I assume that my computation is the same function repeated over and over again, and then I create individual proofs for each step for which I apply that function. Cool. Now, since 2022, we have an extremely high decrease in the cost of applying a Y Combinator in those cryptographic protocols. Repeated computations have become extremely cheap. And the trick here is you do not verify the prior step of a computation. In fact, you just manipulate proof statements. You take two proof statements for two steps, and you create a third proof statement which validity implies the validity of each of the prior proof statements. That is called folding. It's also called split accumulators in the literature. And at the cost of needing a natural recursive form of your computation, it means that we can now do this practically in cryptographic protocols. Cool. So that means that now language definitions can look a little bit smarter. We have a Y Combinator as part of the cryptographic protocol, which means that the compilation to a circuit just needs to be the trace of what? If you're thinking in terms of functional programming language, just one step of the step function of the interpreter. We already define a large class of functional programming language with a definitional interpreter. We gave the semantics with small step semantics that tell us exactly, in the form of a small step abstract machine, how you take any source in that freaking language and how you get to an evaluation. Now, you'll tell me, well, small steps, abstract machines are not the universal model for specifying what a language should do, but thankfully, Olivier Danvy came by and showed us that no, there's actually correspondences between many of the ways of defining how the semantics of those functional programming languages that correspond to a small step abstract machine. So now, the only thing we fundamentally need to express is the step function of an abstract machine. And that's the only thing we need to compile into a circuit. So this is what Lurk has done. We have taken the CEK machine, which is the definitional interpreter for Lisp, and we've encoded all of those rewrite rules in the form of a circuit. Now, that results into saying that Lurk is a Lisp variant that is a relatively fancy iterated CEK abstract machine stepper. We took the step function, wrote it into a circuit. But there are still a couple of problems with this that we're going to go into in terms of obstacles. But before that, let me give you the results. One of the interesting results is that we managed to express this CEK abstract machine in 12,000 constraints in the R1CS arithmetization, to be specific about it. 12,000 constraints, to give you a sense of the size of what this represents, is very small. The SHA-256 hash function expressed as a circuit takes 44,000 constraints. A lot of those constraints are padding, so if you remove all of the padding and just focus on the compression function that is at the core of this hash function, you're really looking at 27,000 constraints. Specifying the CEK abstract machine was writing essentially manually, of course with fancy DSL and all the programmatic tools at our disposal, something that was half the size of a SHA-256 compression function. What does writing an interpreter in the cryptographic context mean? Well, there is some domain-specific knowledge into how to write circuits, translating the modelization of the primitive types of your language, as well as the control structures, into additions, multiplications, and a lot of tricks that we don't quite have the time to go over, but please do see the paper as well as its references for what that represents. But the larger aspect is how do we represent the data structures of that abstract machine? So the CEK abstract machine is so named because it functions with a state that from one iteration to another transports a control term, an environment, and a continuation. The continuations don't start with a K, but I guess CEC was a little bit too confusing for everybody. The idea here is that all of the state management is adversarial. That is, the prover should not be able to fool you as to which program they are proving anything about. So that the other idea is that in this CEK machine, what you're seeing as we write rules on this screen, even if you don't need to read any one of them, is that there are a lot of variables and holes. All of this, in all of the science of writing an abstract machine is about refocusing which subpart of the term we now want to compute on. Now, that pattern matching for us requires forcing the prover to reveal only parts of the program and not the entire program, while directing the prover through the cryptographic protocol about which part of the term they should actually reveal to us, for us, the verifier, to bind them to follow the correct step of the abstract machine. How do we do that? Well, the answer is we hash everything. Rather than passing large inputs, both for passing the state of the abstract machine in general and bounding them to what has been put in them, all of those are authenticated data structures. So the control word, the environment, and the continuation are authenticated data structures bound by, that the prover is bound to by a hash. Every time they tell us anything about those things, they need to prove that they are the correct thing, that is, that hashes to the commitment. And more interestingly, we have those reflected in the language itself, so that the language can now speak about cryptographic protocols and commitments themselves. You can, when you are the prover, evaluating in a REPL, create commitments as well as open those commitments. And then passing a program itself, the term is done through hashing, through cryptographic hashing, using the well-known technique of hash consing. We not only hash everything, but we hash every substructural subterm. Usually this is done in compilers to get cheap equality between values. The way that we do this is, the reason we use this technique is in order to focus some part of the analysis by forcing the prover to give us the pre-image of a particular hash, and that gets us an evaluation of which rule of the interpreter fires that is syntax directed. In Lisp, everything is a cons. In the CEK machine, everything we pattern match against is the head of that cons. If the prover gives us the hash of the tail of the list and the value for the actual input, we manage to fire a rule and validate the correct step for what the prover should be doing at that particular iteration of the step machine, of the CEK machine. A taste of Lurk. That means that Lurk is a legit Lisp. It's a deterministic Lisp. We haven't put all the bells and whistles in there. You do not have a random number generator. But we can definitely define the Collatz conjecture, tell you how many iterations of the interpreter we need, and produce results, as well as produce proofs of those results. What can you do with Lurk? You can write functional commitments. You can write functional commitments that you can now make proofs about within Lurk without knowing anything about circuits or caring about what they are. What that concretely means is that if you have a super secret function that you do not want to reveal, for those of us that are in the American context, or at least the North American context, that would be a credit score function. Right? You're a bank, you're giving a credit score, you're an agency, and you're giving credit scores to a bunch of people, but you don't want to tell them how it's computed. You can now make proofs about how the credit score you delivered to one particular user is fair in the sense that it was computed with the same algorithm that everybody had. We can even do fancy things such as higher order functional commitments that due to time, I will leave you to read about in the paper. And we have build this as a complete system that has a repository, a preprint, and a specification that has already been audited, includes a tutorial, a blog, if this is something that you are interested in making proofs about. I hope that this talk has given you a flavor of how, while we really like Lisp, the generality of the methods we're employing mean that we could possibly have chosen another abstract machine with a few nuances to that. So maybe you're interested in building a proof system for another abstract machine because you care about another functional programming language. Maybe you care about a camel, maybe you care about Haskell, maybe you want to write proof of computational integrity for one of those languages. So there are a few things that we're still figuring out. In the cryptographic context, bookkeeping steps are a lot more expensive than abstract machines assume. Some of the history of the zinc machine for camel, for example, has told us that if you look at the Lisp abstract machines, there's a lot of bookkeeping steps related to passing arguments to function through purification and then thunkification of a short-lived closure that is then passed the argument, that were a little bit pedantic and that was interesting to remove. That is even more true in the cryptographic context. I've told you we bind the prover, we make the prover accountable to every step through a hash. That's costly. So all bookkeeping steps are terrible. The other thing is 12,000 constraints is tiny. We already have a specification of what this circuit should do, which is be a Lisp interpreter. This is ripe for formal verification. Any method will get you a formally verified way of expressing proofs as circuits much faster than compiling circuits one by one. And then finally, the abstract machines that we know and love are very similar in their design. They all function through pattern matching. So there's probably an abstracted general discipline for encoding them to circuits. And in the end, we have a multidisciplinary team with a lot of folks from a variety of backgrounds. We're probably being dunces in a number of aspects. If you have some feedback to share, it would be considered a gift, even if it says in so many terms that we are really being stupid about a couple of things. Thank you very much.
Well, we have plenty of time for questions. Greg, 48?
Yeah, Greg Morissette from Cornell. Very, very cool work. If you relax the assumption about zero knowledge, like if I don't care whether I'm releasing information about the proof, can you take advantage of that in the translation?
Yes, the specifics of the answer require, popping open the hood and looking at what you're doing specifically in the cryptographic protocol. But in general, yes, you are paying a much cheaper cost if you relax the assumption about zero knowledge. Not quite at the abstract machine level, that is. At the abstract machine level, the design looks roughly the same. Your proof still needs a basic notion of correctness, and that is what drives the cost at that level. But that is very true at the cryptographic level, if you relax the zero knowledge requirements. In general, cryptographers know that, and so when it comes to engineering, they very often implement two forms of their system, the costly one that requires the zero knowledge and that use blinding for polynomial commitments, for example, and the cheaper one as well. If you're interested in a system in detail, please come talk to me. I'm more than happy to help.
Chapman, input-output. You mentioned the circuit size. Could you comment on performance in terms of how long it would take to generate the proof and how long to check it for example?
So the general so this gets relatively complex. So we make proof of the Fibonacci function at 1,000 iterations of the Fibonacci function in around 13 seconds, which sounds absolutely horrible. There are layers to this performance. In particular, the base system that we're using to get this cheap recursion is a SNARK. Like all SNARKs, it requires finite fields that are large. The reason being that it relies on the discrete log assumption for those finite fields. We actually do model this using elliptic curves. And like all systems that model elliptic curves, you need to have big fields. I can't go into all the details of this those cryptographic costs, but we already have results of A16Z, Justin Taylor, Georgetown University, etc. this year that show us what we can get a 10x out of this, which means performance is, I think the answer you want is performance for zero-knowledge proof system has been for a long time of the domain of it's too soon. Really, that doesn't work. Proving, verification is great compared to proving, but proving is horrendously slow. We are getting out of that mud pit right now. The proof speed improvements over the last 3 to 5 years, thanks to massive investments in the space, have already not done a 10x, and they are about to do a second one in implementations, for which we already have benchmarks that are sadly not widely distributed. So our system is still a little bit slow. It is built on other systems that we know will improve very shortly.
Thank you. I had a similar question. So you compared the size of the circuit of the interpreter to like the SHA-256 function, but the difference there is that the SHA's function is already flattened, and so you know the size of the program directly correlates to the size of the circuit, whereas the interpreter is being run recursively. So can you hear me or no? Yeah, so because the interpreter is being run recursively, it seems weird to compare the size of its generated circuit to that of the SHA function, because you don't know in advance how many iterations of the interpreter that you run to complete the program. Is that, so far, is that correct? So what I guess I'm wondering is like, is the size, so the proof complexity for generating the proof is known, for example, because for SHA-256, because you know the size of the circuit, whereas you don't know in advance the proof complexity construction for the interpreter because you need to know how many times it runs. But my question is like, well, you could just run the interpreter and see how many times it runs without worrying about the proof, and that would, I'm wondering if you could just directly compute the size of the construction or complexity of the construction in advance by just simply like some simple formula for how many times the interpreter will run.
Right. So again, we're somewhere in. So first, you're completely right. SHA-256 is a computation in and of itself, but there are a couple of slight details about this. For example, what is the size of the input that you're giving to SHA-256, right? SHA-256, that it is a complete computation, whereas what I was comparing it to is the step function of an abstract machine that might run for a large number of steps, and I can predict it, otherwise I would have solved the stopping problem. Right, completely correct. The point that I was saying about this relatively small circuit is, first and foremost, that from a correctness point of view, verifying those 12,000 constraints is looking at a circuit that is much easier to formalize because basically it fits on a metro ticket. That's not a point to effectiveness. The reason why I said it would make things efficient is that we're pretty sure that the circuit is minimal and that it's going to be difficult to make it, insofar as what it is, to make it smaller. The next improvements are in stuff that functional programmers and compiler writers are very familiar with, which is, let's reduce the number of steps that we have to run through, perhaps through modification of the circuit itself. You are correct that this does not guarantee horrible, efficient benchmarks. To give an insight, we run both evaluation and proving. At the moment, proving is 30 times slower than evaluation. So evaluation has nothing to do with circuits. You're just running a Lisp interpreter on a program. The ballpark is, for relatively sensible common task, it takes 30 times the time of evaluation to actually prove the computation, which is terrible if all you want to do is proving. But two things. First, we now know that with the technical lookup arguments, we can make that proving faster by a 10x. Specifically in the conditions in which you are modeling computation over small objects and where you want to pay the cost of manipulating those small objects rather than the one that SNARKs so far has been forcing us to use, which is manipulating big finite fields. Our finite fields are 256 bits. What you want to model in VM is computation of you on double integers, 64 bits, not 256. The 8x blowup is horrible. So next year, we're hoping for 3 times. So proving is 3 times slower than evaluation. And when proving is 3 times slower than evaluation, you get into a range where some applications become really interesting. That is, I may need to run my type checker 3 times slower, but I only run it once because the verifiers will get such a discount on running the prover, an exponentially sized discount, that it will become interesting for them to not have to redo the work. That is, while you're developing your proof of the Faye-Thompson theorem, yeah, you're redoing the type checking yourself, but you're generating the proof. Once you're done, you spend 6 hours generating a proof, ship it to whomever wants to verify it, and then they verify in 10 minutes instead of 2 hours.
Yeah, thanks for going in detail.
Well, I think we should stop here. Thank you again, François.